They're big, they're bad, they're powerful. With the strength to rip stars apart, there's no denying that black holes can be nasty neighbors. But what if the giant sinkholes of space weren't just the grumps next door, but actually pitched in to make the whole neighborhood a little bit more livable? To wrap up our 4-week series on the ins and outs of the place we call outer space, we're looking at the role black holes and their plasma jets play in galaxies. Astronomers around the world have come together to reveal what these beasts are really up to, with the help of ever-improving technology that allows us to see further and further down the road. Need to find an Oreo cookie on, say, the moon? This is what you've been waiting for. Hold on to your hats, we're jumping down the hole. They're big, they're powerful, they're nasty. You and I know them as the giant vacuums of space, but what are they really up to? Today we're talking about the thing that captures everyone's imagination, black holes. I'm Kate from Aalto Communications, and this is the last part of our 4-week series, Way Out There. I'm sitting here with Tuomas Savolainen, an expert in radio astronomy, black holes, and their powerful plasma jets. Welcome, Tuomas.
Thank you. Nice to be here.
Yeah, great to have you here with us. You've been studying black holes and so on for some time. Now, everybody has a sense of what that actually is, but what is a black hole to you?
Well, in a very simple terms, black hole is a lot of mass inside such a small volume of space that the gravitational force that it creates prevents anything, including light, from escaping a black hole. Hence, they are black.
Exactly.
But in order to really understand what a black hole is, we need Albert Einstein. And we need Einstein's theory of general relativity. And Einstein's theory of general relativity tells us what gravity is.
Right. And
interestingly, in Einstein's theory of general relativity, gravity is not a force. It's actually a property of space-time. Mm-hmm. And mass in this theory curves the space-time around it.
So it curves the space-time?
Yes. And in general theory of relativity, space and time, they are interconnected. You cannot separate them. So you get the curvature in the space-time around a massive object. And on the other hand, this curved space-time tells mass, all the objects, light, anything, how they move. And that's what creates a gravity. Mm-hmm. So curvature of space-time telling objects how they move. Now, imagine a situation where you have so compact object that the curvature becomes extreme around it.
Okay, so it's really dense.
Really dense, and then you get a curvature that sort of closes this region out of our universe. You have created a black hole. Mm. And this defining thing about a black hole is the existence of an event horizon. We call it an event horizon. It's kind of a one-way membrane in the space-time. You can go in, but you cannot come out. Because after you've gone in, then all of these paths in the space-time, they are just pointing inwards. You don't have any path outwards. You can try to go outwards, but you will end up going inwards in the black hole. So this is a weird, this is a mysterious object.
Definitely.
Well, how do we create a black hole then?
Yeah, that's a great question.
As I said earlier, you need to squeeze matter into a very dense volume, and in order to get an idea how dense, how small a volume you need, you can take our sun.
Yeah, the one that we see every day, hopefully.
Yeah, which weighs quite a lot. Mm-hmm. If you squeeze all the mass of the sun inside a sphere which has a radius of about 3 kilometers.
Okay, yeah.
That's roughly the size of the central part of Helsinki, the Helsinki city center. So if you squeeze our sun inside the Helsinki city center, you have created a black hole. So 3 kilometers is about the distance from the central railway station to Pasila station. Now imagine that you are in a train coming from north. If you stop at Pasila, just outside of this newly created black hole, you could still go back towards north. You could turn the train around and go back north.
You say, that looks too scary.
Yeah.
I'm going back.
But if you come just inside of the Pasila station, then you are inside the black hole and you cannot escape the Helsinki city center anymore.
So Helsinki city center is going to swallow you. And that's it.
Yeah.
No coming back.
So squeezing about the mass of our sun inside a sphere of about 3 kilometers in radius, and you have a black hole.
So that's the recipe to make one. Now, I think most people are resonating with the fact that it's black, it's a hole. Kind of hard to see those things. How do we see them in space? Because that's something that seems a bit of a mystery to me.
You cannot, that's right, you cannot see the black hole itself, but you can infer its presence based on how it affects its surroundings. So there are some ways to do this. The earliest observations that we got that sort of point towards there being black holes in our universe are observations of quasars. So these are centers of galaxies, so centers of pretty distant galaxies where there is a supermassive black hole in the center, and it's actively feeding on matter. So when this matter gas is falling into the deep gravitational well of the black hole, it creates this kind of a whirlpool around the black hole, reaches very fast speeds, significant fraction of the speed of light, and it heats up because of the friction in the disk. So different parts of the disk moving at slightly different velocities, going very fast. You get a lot of friction, you get a lot of heat, and they shine extremely brightly. In fact, these quasars, when they were first found, they were really a major puzzle because they looked like stars, but they were in galaxies very, very far away. So there was something compact, very compact, which was brighter than all the stars of the entire galaxy.
Okay.
So this central part, this black hole there, was outshining the whole galaxy. And astronomers needed to think, okay, what kind of object can create that kind of a brightness? It cannot be stars. I mean, the nuclear fusion wasn't just efficient enough to create this amount of energy that was needed. But it turned out that accretion, we call this phenomenon, accretion of matter on the black hole, actually can liberate energy much more efficiently than nuclear fusion, and they can power these things.
Right.
And this is not the only thing about the quasars that we can see. Some of them also produce plasma jets which shoot out from the immediate vicinity of the black hole and can extend large distances. They can go beyond the confines of their host galaxy.
Right.
So I think we will come back to this later, but this is one way of seeing the influence of black holes.
Yeah.
Another way to see the influence of the black holes is that if we can measure the motion of things, like for example stars, around the black hole.
We actually have a clip of this.
Yes, I think that's based on real observations of the orbits of the stars in a small stellar cluster in the center of our Milky Way, where astronomers have been able to measure the orbits of the stars around the supermassive black hole in our own galaxy.
Right.
And what can be deduced from this is that if you can measure the full orbit, you know then how long the orbital period is, how long it takes for the star to go around.
Right.
And you can measure the size of the orbit. Then you can use Kepler's laws, centuries-old physics, just to determine how much mass there has to be inside that orbit.
Yeah.
And in case of our own Milky Way, it's 4 million solar masses.
4 million solar masses.
4 million solar masses in a very tiny volume of space. And this mass is also coincident with an object that we call Sagittarius A star, which is not a star. It's a source of X-rays and radio emission, so very unlike normal stars of the Milky Way. And we think that this is the black hole in the center of our galaxy.
Okay, and you can see that because you see the stars going around it.
Yes,
you really see it's avoiding.
We know the effect that this 4 million solar mass thing creates on the stars going around it.
Yeah.
And even there are even further observations of this. So scientists have been able to measure also the motion of gas around there and so on. So.
And so you mentioned that this was in the center of our galaxy, the Milky Way. Now, this is something that probably we want to get too close to, but we can get somewhat close because the stars are also avoiding it.
Yes. So for the stars, they can happily go around the black hole unless they come too close.
Yeah.
If they come too close, what can happen is that tidal forces, so basically the fact that the gravitational pull on one side of the star is significantly larger than the gravitational pull on the other side of the star, can rip it apart. But that happens only if the star comes too close to the black hole.
Yeah.
And also it needs a certain size of a black hole to be an efficient mechanism. But if that happens, the star gets ripped apart, and then the black hole feeds on the gas, on the remains of the star.
Right. Now, there's one word that you used a little bit earlier, and that was supermassive. And that's something that's used in connection with black holes quite often. What makes a black hole supermassive, or what is a supermassive black hole?
Okay, well, I think we should discuss about what kind of black holes are there in general.
Yeah.
And we know of two kinds of black holes. There are so-called stellar mass black holes, and these are born when a massive star comes to end of its life. So let's take a giant star, which is, let's say, 20 solar masses or more massive. When it comes to the end of its life and the nuclear reactions inside the star stop because it has used all the fuel it has to keep those nuclear reactions, that nuclear fusion going on, then that there is no more pressure coming from those nuclear reactions that would push against the gravitational pull that tries to squeeze the outer layers of the star towards the center. So there's no more pressure there in the core that would push against it. And the star becomes unstable and it implodes.
Okay.
What happens there is that then this implosion bounces back. You get a supernova, so the outer parts of the star are shattered. But in the center, you get something very compact. It collapses under its own gravity. And when a normal star like our sun will end its life, it also will have the central parts collapsing, but they won't become a black hole. They will become a white dwarf star where there is just a new balance. The electrons in the matter there, they will create a pressure that keeps the white dwarf from going into a black hole. But if you have a very massive star, then this gravitational pull is large enough so that you don't get any more any pressure that could stop that collapse, and those internal parts just collapse until a black hole. So that's how you can create a stellar mass black hole.
Yeah.
But then there are also a whole other class of black holes which we call supermassive. And by supermassive, I mean black holes with masses from millions to billions of solar masses.
So of our sun, a millions or a billion even?
Yes. And these are in the centers of galaxies. Actually, we think that there is likely a supermassive black hole in the center of every massive galaxy. And they seem to evolve together with the galaxy. So they grow hand in hand. And those quasars that I mentioned, they are those supermassive black holes in the centers of galaxies, just happen to be actively feeding, so actively accreting.
Right. So they're active there, they're doing stuff, and they're quite common in a sense if they're at the center, or presumably at the center of every large galaxy.
Yes, and we, as quasars or as active galaxies, we see maybe 10% of them. Others are quiet, they are dormant, they are not getting a snack right now, so they are just sitting there, not creating a fuss.
Right.
But we see the loud ones.
Yeah, okay. So they're the ones who are getting your attention for now.
Yeah.
I want to ask you about the biggest misconceptions about black holes, because I think most people have a sense of what they are and what they do, and they're the grumps on the block. They're a little bit dangerous, like we've already talked about. But what is it that you get asked a lot? What is it that people think about black holes that doesn't really sit right?
Well, I think the most typical misconception is that there's some kind of cosmic vacuum cleaners that suck everything in, so that if there is a black hole in our galaxy, people are afraid that, okay, well, is this the end?
Are we going to get sucked in?
Are we going to get sucked in? And no, they are not cosmic vacuum cleaners. You only get in trouble if you get too close to the black hole, and you really have to get very close in order to get in trouble. Yeah. And the distances between the stars and the galaxy, they are vast. So a black hole has in its so-called sphere of influence only a very small fraction of all the stars in our galaxy. So if we think of the central black hole in our galaxy, its gravity controls the motion of maybe 100 stars. It's a tiny, tiny fraction of all the stars in our galaxy.
Yeah.
For all the other stars which are further away, the combined gravitational effect of everything else in the galaxy is much stronger than the gravitational effect of the black hole there in the center.
Despite the fact that it can be incredibly powerful.
Yeah. So that's one thing. But let's just look at those 100 stars in a little bit more detail. And what happens there is that for most of them, actually for all of them at the moment, they are not sucked in by the black hole. The black hole just acts like any other mass, any other object with the same mass, and its gravity makes the stars to go around it, and they happily go around it, and they are not ripped apart.
Right.
Only if there is some kind of a perturbation in the system, so that the star gets a little bit off from its orbit, it can come too close to the black hole, so it gets ripped apart, or its trajectory gets into the event horizon. So no, they are not cosmic vacuum cleaners.
Yeah, well, that's a very good thing to clear up, because I think that is what most people conceive of when they think about black holes. So it's great that you're here to set us straight in our thinking. I guess the bigger question, we've talked a lot about now, what are black holes, how can we see them, what function do they play, a little bit we've gotten at. Why do you think that we need to study black holes? Of course, space exploration and understanding space is very exciting. It's an incredibly attractive feat in and of itself to be able to learn about our universe. But what is it for you that you think, why is it that we need to study black holes in particular?
I think the most important thing about studying the black holes, besides the fact that they are really cool objects out there,
Indeed.
is that they may give us a chance to test general relativity in very strong gravitational fields.
Yeah.
So Einstein's theory of general relativity has been tested in the weak gravitational fields extensively, and it has passed all the tests with flying colors. But we know that the general relativity cannot be the ultimate theory about nature, because it doesn't come along with the theories of our other fundamental forces in the nature. So general relativity doesn't work well with quantum mechanics, which then describes other forces in nature, electromagnetism, weak and strong nuclear force. So in order to be able to combine these into one coherent picture, we need something deeper than general relativity. And that's why we need to test it. We need to see where are the limits of the theory, where it might break down. And can we get some clues about the physics beyond it. And black hole gives a cosmic laboratory unlike anything else, because there the gravitational forces really are the strongest sense.
So they give you a huge opportunity.
Yes, so it gives a huge opportunity for fundamental physics if we can make tests of general relativity near the black hole.
Yeah.
And I mean that's really fundamental research.
Yeah, absolutely. And there's the cool factor too, like you mentioned, they're just really cool things, very exciting things, unlike what we find elsewhere. I know that you've been studying black holes and their plasma jets for some time, and I was hoping that you could tell us a little bit about that work and what it means. So you touched on it a little bit earlier, but tell me again about what a black hole and a plasma jet does.
Yes, so some of the black holes, when they are accreting matter, seem to be able to not only suck in this matter that comes too close, but also to shoot some of it out. And we see these jets of magnetized plasma that are formed. They're very, very close to the black hole, but then they shoot out the matter at speeds which are close to the speed of light, so they are very efficient in accelerating the plasma into very high speeds. And these jets, they can travel vast distances, so they can be as large as a million light years in the extent. So
they're actually shooting this matter, the energy, out that far?
Yes.
A million light years?
Yes, they can go outside of the host galaxy,
into
the intergalactic space.
Right. So if there's a black hole at the middle of each galaxy, some of these are capable of pushing their plasma out well beyond the borders of their own galaxy, which is quite impressive, I think.
Yes, and this has been noticed over, let's say, past 20 years that this may actually have something to do with the way that galaxies evolve. So the astronomers have noticed that their theoretical calculations about how much massive galaxies should produce stars are not matching with what they observe. So in massive galaxies, one would expect a lot more star formation than we see. And in order to form stars, you need gas to cool. When it cools, it starts to collapse and forms these clumps from which the stars form. And this does not happen at the rate that our theories and simulations would predict. So it looks like that there is something that keeps that gas from cooling enough.
So there's a kind of galaxy heater of sorts.
Galaxy heater, galaxy thermostat or something. And one of the best candidates for this role are actually black holes and these plasma jets, which then can push out the matter. They can apparently heat somehow the matter mechanically, this gas mechanically. We don't exactly know all the details of this mechanism yet. What we don't, for example, understand yet is why how these very narrow jets, they are really narrow and collimated, how they couple with this matter in a galaxy scale. So how you are able to heat something by just a very narrow pencil-like beam. But apparently this is happening.
Yeah, so there's some kind of very supportive function that they're playing.
Yes,
or it seems so, at least.
It's more like that they are shaping the way the galaxies look like. So that if we wouldn't have them, we would have a very different looking universe. Many more really massive galaxies, which would have a lot more stars in them, a lot more star formation. So the universe would look different
than what we actually
are actually seeing.
Yeah, I think that's incredibly interesting. It speaks to the kind of unexpected role that they're playing in the formation of galaxies and our understanding of the universe as well. So definitely very interesting. I wanted to move on to the kind of telescope that you're using when you carry out this astronomical work. So how do you actually see these things that you're studying?
Yeah, so I should say that I'm mostly interested in understanding how these jets form in the first place.
Yeah.
So that's what I've been studying. So I need to see very, very close to the black hole.
Yeah.
And I'm also interested to see, in general, what happens in the immediate vicinity of the black hole. So since black holes are small in astronomical terms.
In astronomical terms, maybe not human terms.
They are small in size, and these actively accreting black holes, these quasars, active galaxies, which we observe, they are also far away. They are far away in the cosmos. So what we need is a lot of angular resolution. We need to be able to see very fine things. And well, a good example here is that I think we will come back to this later, but there is a project going on which tries to take an image of the shadow of the black hole in the center of our galaxy.
Yeah.
And the size of that black hole in the center of our galaxy, the apparent size of the sky, corresponds to something like a Oreo cookie in the moon seen from the Earth.
Okay, so
or thickness of a human hair in Tallinn seen from Helsinki. So
Yeah.
it's incredibly small. And it's in order to put this into perspective, this is something like 1,000 times smaller, 1,000 times finer than what can be resolved with the famous Hubble Space Telescope.
the one that gives us gorgeous images.
That gives us gorgeous images in optical wavelengths. But we need much higher resolution. And there is one technique in astronomy that can give us that resolution, and that's called very long baseline interferometry. It's a technique for combining radio telescopes that are far apart into a single instrument that has resolution corresponding to a telescope that would have the same size as the distance between the furthermost telescopes in this interferometric network or array.
So what does that mean in practice when you put them all together?
So in practice it means that we have a collection of radio telescopes all around the globe, in different continents. We observe simultaneously with them. So all of them are looking at the same source at the same time. They record the signal, and there is a very accurate atomic clock at every site, which is used for timekeeping, which is used for time stamping those recordings, so that we can time this whole array very accurately. And then we will take these recordings. The recordings are typically nowadays hard drives, so there are packs of hard drives, and we take them to a specialist supercomputer, which we call correlator, and there those disk packs are played back. They are synchronized based on those timestamps that are in those recordings.
From all these places in the world.
All these places in the world. And then we create kind of a virtual telescope in a sense, or we recreate the situation that was in this electric field throughout the globe during the observation in a computer. And what we get from this is we get an equivalent of a radio telescope size of the Earth in terms of angular resolution.
The size of the Earth.
The size of the Earth.
That's pretty big.
Yeah. Of course, that's not the limit. We can extend this same technique to even longer baselines and go to space. So we can put a radio telescope on board a satellite and put that around the orbit, put that on orbit around the Earth, and do the same thing.
Yeah.
Use the radio telescopes on the ground and on the satellite, and create a radio telescope which has an angular resolution corresponding to a telescope that corresponding to a radio telescope which size would be hundreds of thousands of kilometers. So that's actually something that has been done. There is a Russian radio astron mission that's doing this. So they operate a 10-meter radio telescope on the orbit around the Earth, and the orbit is pretty high, so it goes almost all the way to the moon. So the longest, we call it the baseline, the longest separation between the telescopes on the ground and between this orbiting one is about 350,000 kilometers.
Not too shabby.
No. So that can give us this angular resolution.
And with that, you have power. You can see.
We can see the sites where we can see very close to the sites where the jets are born.
Right.
For example, last year we were able to image the formation close to the formation site of one jet in the galaxy, which is about more than 200 million light years from us, and we could see regions there which are just about 100 times the size of the black hole in the jet. So we are getting very close to the region where the black hole itself is.
Right, getting closer and closer.
Yeah. So we can study the mechanisms that are creating these jets by, for example, taking computer simulation of a formation of a jet and then comparing, do they produce the same shapes as we see in these observations or not?
Yeah, it strikes me that this is the kind of work that wouldn't have been possible that long ago, that probably has developed quite significantly in the last decades with computing power and so on. But also this idea that with this special technique of combining the radio telescopes around the world, that essentially requires a vast amount of international collaboration.
That is correct. This very long baseline interferometry technique is fully based on international collaboration, because these observatories, these radio telescopes that participate, they are run by different universities, different research institutes in different countries. So you have to bring together a lot of people from different countries, different cultures, and so on. So it's really a global effort.
Yeah, and I think that the Event Horizon collaboration is one excellent example of this, and you have a very, very big goal in mind with that.
That's correct. So Event Horizon Telescope collaboration is a collaboration of about 200 scientists. And this collaboration is equipping existing millimeter wavelength telescopes. So when I was talking about this radio astronomy mission, for example, where I was talking about centimeter wavelength radio waves. Now we are now moving to shorter wavelengths, millimeter wavelengths, and Event Horizon Telescope collaboration is equipping existing millimeter wavelength telescopes with this very long baseline interferometry equipment, and they are creating, or we are creating, also part of the collaboration, we're creating a millimeter wavelength, a very long baseline interferometry array that has global proportions. So there are telescopes in the US, there are telescopes in South Pole, in Chile, Mexico, in Europe, one coming up in Greenland. And the aim of this whole collaboration is to try to take an image of a black hole.
For the first time.
For the first time.
Yeah.
And what we are trying to see is something called the shadow of a black hole. And it's what it's about what the black hole's gravity, so this massive curvature of space-time, does to the light rays that pass close to it, not going into the event horizon, but just a little bit outside of that. They get massively curved, their trajectories, and this is something that we call a gravitational lensing. So the gravity affects how the light moves around the object. And what happens is that you create this kind of a bright photon ring around the black hole, which has a diameter of about 5 times so-called Schwarzschild radius of the black hole. That's that radius that we were talking about in the beginning, inside of which you need to push the mass in order to create a black hole. Yeah. So about 5 times, the diameter of that ring is about 5 times the Schwarzschild radius, and inside there should be just a very black patch and bright ring of radiation around it. So that's what the theory predicts.
Right.
And it turns out that the size of this ring is just observable. It's just big enough so that we could resolve it for the black hole in the center of our own Milky Way, and for another black hole in a galaxy, M87, which is a little bit further away, but it's also much more massive black hole. And these two have an apparent sizes for this ring, this shadow.
So you know that you could capture it.
We could capture it,
Yeah.
and that's what we are trying to do with the Event Horizon telescope.
Yeah, well, it's definitely a very ambitious project, but something that will reap big rewards, I have no doubt. So we can expect something hopefully sometime soon, I hope.
We had the first observations in 2017, and we have been busy crunching the data, busy calibrating it, and trying to make a very careful analysis of the data. And I hope that the first results will be announced or published sometime in the first half of this year.
Yeah, well, we'll all be waiting for that, I'm sure. I think this is a great way to end this, just thinking about a fuller understanding of our universe really relies on a collaboration, international networks, and also a curiosity for something new and trying new things and pushing technology further so we can get a better understanding. So thank you so much, Tuomas, for being here today and sharing all your experience and expertise about those nasty beasts that we know from space, black holes. This is the last part of our 4-week series, Way Out There. Thanks so much to our audience for tuning in and following along as we've discovered these wonderful topics along the way. Until next time. Looking for a fresh approach to science and research? Subscribe to Aalto University's YouTube channel.